Hello everyone. I just wanted to make a video for you to kind of go through what it looks like to take the limit as n goes to infinity of our Riemann sums in summation notation. So this kind of puts together a lot of the things that we've been working on in section 5.1. And that's kind of why I wanted to go through it with you, because it does connect a lot of things. And it's also going to help us figure out kind of what's happening in the background of the things that we're going to be doing next week. So again, just want to kind of reiterate some things. So Riemann sums, what we're doing is chopping our area up into these vertical bars, and we're cutting them up into equal pieces, right? So the width of each of our bars is delta x, that's what we call it, and you calculate that with b minus a over n. And then you label your endpoints. The leftmost endpoint is always x sub 0, and then x1, x2, x3, and so on and so forth until x sub n is our last one. So x sub 0 is always a, and x sub n is always our b value. And then if I wanted to calculate any specific x value in between, like x sub 3, say, we talked about this on Wednesday, that this is how we can find that. So any kind of intermediate value. So here, x sub 3 would be x sub 0, right? This first x value plus 1, 2, 3 delta x's, right? And I could do that for any of these. I could do it for x2, for x4, but this is kind of the direct way to find any of my x values without labeling all of them. And you'll see why we need that in a minute. So again, x sub 0 plus I, which is whichever x value we want to calculate, times delta x. And again, x sub 0 is a, and this delta x is b minus a over n. So I just kind of plugged everything in to get here, and I'm going to use this in just a minute. So that's kind of a nice closed formula for each of our x sub i's. And then we calculate all of our areas by doing width times height plus width times height plus width times height, or we can factor that delta x width out. Okay, and then today we got summation notation, and we put our Riemann sums into summation notation, and they look like this. And so we'll use these in just a minute. These are like a nice a shorthand form for all of, going back up, all of this mess. The summation notation makes it a little bit easier to write everything out. And we said that if we took the limit as n goes to infinity of our Riemann sum, we would get exact area. And then we mentioned these power sums and practiced a few examples of that. Okay, so I want to do this example where we find the area, I'm calling that area A, under the graph of f of x equals x over the interval from x equals 0 to x equals 4, and find it in 3 ways. I'm just going to go through the second, which is the limit as n approaches infinity of the right Riemann sum. You'll get the same thing with the left Riemann sum, but dealing with some of the summation notation just gets a little messier there. And we're going to get the same answer, and the process stays the same. So I'm just going to go through the right Riemann sum so that you can see what that looks like, and just know that you would get the same answer out of the left Riemann sum. And we'll use geometry as well to double check our answer. Okay, so let's start by finding the limit as n goes to infinity of r sub n. All right, so first of all, what I'm going to do is I'm just going to find r sub n by itself, and then I'll take the limit as n goes to infinity of that. Now, r sub n is a right Riemann sum with capital N. intervals or capital N rectangles. And right here is our formula for R sub n. I'll go ahead and just use this one with the delta x still in it. So my right Riemann sum with n intervals is the sum from I equals 1 to n of delta x times f of x sub I. So that's what my right Riemann sum looks like. And let's see, delta x. We know how to find that. And so I'm going to switch gears and we're going to do a little of the background work. Switch to this color. Okay. So with Riemann sums, we always kind of start by calculating delta x first, right? It's b minus a over n, which is the number of rectangles. Here, my number of rectangles is a capital N, so I'm going to use a capital N instead of that lowercase n that we used before. And so here, my b value, again, comes from my interval. B is 4, minus my a value, which is 0, all over n. I still don't know what n is. We're going to keep n general here. And so that means my delta x is 4 divided by however many rectangles we have. So that's my delta x. So that will go in here in just a minute. And then f of x sub I. This is where this x sub I being equal to a plus I times delta x is going to come into play. I just mentioned that a little bit. This is how we can find any specific x value that we want. And again, I can just kind of use what I have here to find a nice formula for any x value I want. So my a value here is 0, so I'm going to plug 0 in for a, and I'm going to add to that I times delta x, and we just found that delta x was 4 over n, so I'm going to go ahead and plug that 4 over n into my formula here for x sub I. So 0 plus I times 4 over n turns into 4I over n. This is how I'm going to represent any x sub I that I want. And my delta x is 4 over n. So then I'm going to come back to my Riemann sum here, and I can plug all of this in. So my Riemann sum here is going to be the sum from I equals 1 to capital N. Delta x, which I just found, was 4 over n, times f of x sub I, and we just found that x sub I was 4I over n. Okay, and I know what f of x looks like. F of x is y equals x. So if I take x equals 4I over n and I plug it into my function, then what comes out is y equals that same x value, 4I over n. So I'm going to go ahead and evaluate that. I equals 1 to n. 4 over n is still my delta x, and f of 4I over n is just 4I over n. And then from here, I can just work on simplifying this. So I've got a sum from I equals 1 to n of 16I over n squared. Now, to add this, my variable here in the sum is I. This is my counting variable, and that is the only variable in this sum. This n down here, the number of rectangles that I have, isn't a variable as far as my summation is concerned. So I can pull anything that's not an I out of this summation. And so that 16 over n squared is a number as far as this summation is concerned. And so I can pull those out of here. And all I have left in there is that I. And this sum from I equals 1 to n of I, that's one of these power sums. And I can go ahead and use this idea to plug in there. So the sum from I equals 1 to n of I is going to be n squared over 2 plus n over 2. So I'm going to go ahead and plug that in for my sum here. And so I'm going to have that 16 over n squared that we just pulled out times n squared over 2 plus n over 2. And now I can just distribute this here to simplify. So when I take 16 over n squared times n squared over 2, you can multiply across. You'll have 16n squared over 2n squared plus 16n over 2n squared. And we can simplify those. These n squareds cancel, and I'm just left with 8 here, plus 16 over 2, that's also 8. N, this one n on top cancels one of those on the bottom, and I still have an n on the bottom. So that over here is 8 over n. I'm going to rewrite that because that looks a little funny. Okay, that looks better to me. Okay, 8 over n is how this guy simplifies. Okay, so this is what r sub n simplifies to. And I want to take the limit as n approaches infinity of that. So the limit as n approaches infinity of r sub n is the limit as n approaches infinity of this thing that I just found, 8 plus 8 over n. Well, as n goes to infinity, 8 is just 8. And as n goes to infinity, 8 over n, this goes to 0, because as I take 8 and I divide by bigger and bigger and bigger numbers, that whole thing gets smaller and smaller and smaller, and that heads toward 0. And so what I get out of this limit is 8, which means that is the area between the graph of y equals x and the x-axis over the x values from x equals 0 to x equals 4. This is the exact area, and it's exact because I took the limit as n went to infinity of this Riemann sum. This is my area with an infinitely many rectangles, so I don't have any estimating at all. Now, I want to do this third one here, this number 3, which is I want to check this area using geometry. Well, to use geometry, I have to figure out what this looks like. So this represents the area under the graph of y equals x. Y equals x. I know what that looks like. Put it over here. Y equals x, that's a line. It goes through, right, my y-intercept is 0, so it goes through the origin, and I have a slope of rise over run of 1. So that's how I knew it's this line right here. And I want the area underneath this graph. That means between this graph and the x-axis, from x equals 0 to x equals 4. So I'm going to go from x equals 0, that's right here, to x equals 1, 2, 3, 4. And so if I keep extending this, the area between this line and the x-axis is all of this area. And again, I'm going from x equals 0 to x equals 4. This is the area that I want. And this is area that I know how to find. This is a triangle. I have geometry to find the area of a triangle. This side of my triangle has a length of 4 because I go from 0 to 4. And y equals x, so this point here is 4, 4, which means the height of this triangle is also 4. All right, let's see how your geometry is. How do you find the area of a triangle? Well, it's 1/2 your base times your height. So we're going to have 1/2 the length of our base is 4. And the height of our triangle is also 4. Multiply all of that out, and you get an area of 8, which is exactly what we found above. So that's kind of what this process of finding the limit of a Riemann sum looks like. You use these formulas that we created on that very first day of a Riemann sum. You plug them into this beautiful summation notation, plug your x sub I formula into your function, whatever your function is. So for instance, if I had y equals x squared, if that would have been my function, then f of 4i over n would have been my x value, which is that 4i over n squared. Does that make any sense? That's kind of how we do this. You'll plug it into your function. Here, y was equal to x, so we didn't have a ton of work to do here. But if our function was something different, we would have had a little bit more work to do. So I just wanted to kind of make that clear in the process, because I know y equals x is kind of a funny function to be trying to figure this out with. But it was something that we could find the area of here. And then once we plug that into our function, from here, we are just evaluating this sum. And so you'll multiply everything out, pull your constants out, and then use these power sums to simplify. And then once you're done, you will get an expression just with n's in it. And you take the limit as n goes to infinity of that thing. And you get your perfect exact area. And then we checked it with geometry. So I hope that helps kind of wrap things up and connect some ideas for you in section 5.1. You're not going to be tested over this. I just wanted you to see it once and try to kind of see what was happening in the background, because we are going to find another way of kind of, it's almost like a shortcut. Do you remember how when we did derivatives, the limit of the difference quotient, right? The limit definition of a derivative was our long way, and then we got derivative rules as a shortcut. This is kind of our long way, and next week we're going to get a shortcut to figuring out what this exact area will be. So I hope that helps, and I will see you on Monday. Have a lovely weekend.